We cannot process an infinite amount of data. We might think that we are continuously looking through our eyes, but in fact our brain is sampling what we're seeing. We don't actually see a continuous picture, but a sampled version. We can think of the output of a microphone as a voltage waveform, which we can plot voltage versus time, just like what we might see on the oscilloscope if we connect a microphone up to one in the lab. To process this signal digitally, we must first convert it to the digital domain. This requires some kind of sampling. Traditionally, sampling would be done in the time domain. We break up time into discrete intervals, and at regular intervals we take a measurement, see what value our voltage is, and that's the number which we represent by x of k, which we can operate on. Now, for technical reasons, as you'll be well aware, we can't store a real number in a computer. That means that if this number were exactly pi, we're not going to be able to store 3.14159265358979323846643 going on forever. We can't possibly store that in our computer, so we have to round it off. The errors that you get when you round off are called quantization errors, and they would be considered in a second course on signal processing. For us, we don't have to worry about that for now. The more important thing to worry about is what this loss of information means. The red signal contains all the information. We're only sampling it. We are losing information. Starting with our original signal x of t, we sample it using an A to D converter and a sample and hold process, which we won't worry about, to get our sampled signal x of k, where k is an integer. Now, depending on how fast we sample the signal, x of k contains snapshots of our voltage waveform up here at regular time intervals. Capital T is the sampling period, so 1 on t is the sampling frequency. The fundamental question is, given these samples x of k, is it possible to go back and recover x of t? Information has been lost when we're sampling, so this will be impossible in general, but maybe if we make additional assumptions about properties of x of t, this might be possible. This fits in nicely with our bigger question. We started by looking at a signal x of t, going through an A to D converter, processing it in a DSP block to a D to A converter, getting y of t in part 1. In part 1, we asked two questions. The first was how to figure out how does this system transform x of t to give us y of t. And the second question was, if we wanted to process x of t in a particular way, how do we design our DSP block here? An even more fundamental question is, if we ignore the DSP block here and just have our A to D converter, which does this sampling up here, and a D to A converter, which attempts to reconstruct a signal based on its samples, is it possible for y of t to be equal to x of t? If we can't even do this, then digital signal processing might not have much use in the real world, because we can't even recover our original signal, much less do interesting things to it. Even though the sampling operation is not time invariant, it turns out that we can understand it very well by looking at both the time domain and the frequency domain. In this chapter, we will look at time domain sampling and look to see what frequency domain information tells us. And then in the next chapter, we will look at sampling in the frequency domain. Due to the duality between time and frequency, we expect to see very similar things occurring. In one sense, recovering the original signal x of t is intuitively very straightforward. Given these sample points, all we need to do is fit a nice smooth curve through it, and then we can say that represents our original signal. The challenge is that there's more than one way to draw a curve through these points. Nevertheless, we are inclined to believe that some ways of drawing lines through these points are more sensible than other ways of doing it. Looking at the red and the white lines and seeing that there's not much difference between them lets us suggest that if we introduce an extra condition, such as assume the original signal is varying slowly in time, then even if we don't get a unique answer, we should get an answer that's very close to the original solution. In fact, it will turn out that if the original signal is sufficiently slowly varying in time, technically, if it is band limited, then we can recover it exactly just from these samples. That's quite amazing, because our original signal x of t in any finite interval, such as between 0 and capital N, takes on an infinite number of values. By which I mean we have a value at x of 0, a value at x of 0.1, a value at x of 0.05, and so forth. We can keep subdividing this interval into finer and finer regions, and x of t can take on whatever value it likes within all these regions. So somehow, even though we have compressed this infinite amount of information into just a finite number of numbers, we are still able to recover what this original signal is under certain situations. There are two ways of deriving a technique for how to reconstruct the signal x of t from its samples x of k. In actual lectures, what I would do is I'd take a longer approach, but a more intuitive approach, where we first study discrete time systems, learn about the discrete time Fourier transform, and in that way we actually get to see how we can reconstruct the original signal by thinking about what happens when we take sinusoids and sample them, and how we can reverse that procedure. However, in textbooks there's a faster way of getting to the heart of the theory, and it's this summary that I am going to be taking here. So it might look like a little bit of a mystery why it works, but the main point is we see that it's easy to understand, and it does work, and it is insightful. So we just overlook the fact that it may look a bit magical. Watch carefully, because here's the magic. From our samples x of k, we form this signal x of t. This is not my original x of t, this is step 1 in the reconstruction process. I just don't want to write tilde over x the whole time. So, given the samples x of k, we just add a Dirac delta function to each one. Graphically, all we are doing is forming our x of t by putting in these Dirac impulse functions at our sample points. Of course, k goes from negative infinity to infinity, and so there's an infinite number of points that we're going to be fitting these Dirac delta functions to. You might think this is a silly thing to do, but if nothing else, what it does is it at least returns us back to continuous time. You see, our samples here are in discrete time, and the very first thing is we need something in continuous time. Then we can apply a Fourier transform to it, for example, to try to understand if this reconstructed version contains any information about the original version that's useful and that can be extracted. Besides being back in continuous time, there are two other features this reconstructed signal has. The first one is that it essentially agrees with the sampled data at the sample points. Now, why don't we just have x of t equaling a finite value? Why have this Dirac delta function in here? Well, when we come to compute the Fourier transform, if we just had isolated numbers in here, when we integrate we will get 0. So this delta function is to make sure that when we take the Fourier transform we get something interesting. The other feature this has is that it fills up the lack of information with zeros. Our original signal contains a lot of information. We only observe it at these sampled points. In between, we don't observe it. So what value could we give to x of t between sample points when we don't observe it? Well, 0 is actually not a bad idea. We don't know what value to give it, so why not just give it 0? And this is exactly what this expression is doing. You may be asking, where exactly is the magic? Well, the Fourier transform of this reconstructed version actually contains a lot of information about the Fourier transform of the original signal x. This is not obvious at all just by looking at this, but when we go through the maths, we see a very striking relationship and an important one. And bam, here is the magic. On the left is the Fourier transform of our reconstructed signal. On the right is the Fourier transform of our original signal. We see that the Fourier transform of our reconstructed version is given by this infinite sum which only contains the Fourier transform of our original signal. Specifically, we are just summing up shifted copies of the original spectrum. So when n equals to 0, we have the original spectrum here. When n is equal to 1, we have our original spectrum shifted to the left by 2 pi. and so forth. We shift the spectrum to the left and to the right, and we just add up all these copies. Notice that I'm assuming throughout that the sampling period is equal to 1 to make life a little bit easier. If my original spectrum looked like a triangular pulse from minus 2 pi to 2 pi, then according to this reconstruction formula, the Fourier transform of my reconstructed signal will look like this, plus a copy of it shifted by 2 pi, which means I need to add to it this, plus a copy shifted by 4 pi, plus a copy shifted by 6 pi, and going in the other direction too, a copy shifted by negative 2 pi, negative 4 pi, and so forth. In this particular case, when we perform the summation, we find that the spectrum of the recovered signal is just this constant line here. For example, at this point here, I'm adding 0 and let's call it 1 together. At this point here, I'm at a half for both signals. I get 1. At this point here, it looks like when I add these 2 points, I get 1 and so forth. So by adding these overlapping copies, I end up with a spectrum that looks like this. Now, you may well say, that's got nothing to do with the original spectrum. The original spectrum is the one hidden down here in white, and the recovered spectrum is just this straight line here. Well, visually that's true in this example, but remember, there is a very close relationship. It's given by this equation here. And moreover, the only reason we ended up with a different spectrum here is because there was overlap. If we do not have overlap, then we can actually recover the original spectrum. Let's have a look at that now. In this example, I've been careful to make sure that my original spectrum lies fully between minus pi and pi. Outside this region, it's equal to 0, and in fact, right on the boundary, it's equal to 0 too. This means that when I create these shifted versions of it, they occupy regions outside of minus pi to pi, and then when I perform this summation, they do not interfere with each other. That means that if I know my original signal has a spectrum between minus pi and pi and is 0 outside of that region, then when I do my reconstruction like this, I get a signal x of t whose Fourier transform contains, between minus pi to pi, the exact Fourier transform of my original signal. In particular, all I have to do is take x of t and pass it through a low-pass filter. Remember, a low-pass filter, an ideal one at least, has got a frequency response that looks like this. Minus pi to pi, it's equal to 1 and it's 0 elsewhere. And if I filter a signal in the time domain, that's the same as multiplying its frequency response by the frequency response of my filter. And if I multiply something by this low-pass filter, then it will keep whatever's in the region between minus pi to pi and set everything outside that region to 0. Therefore, I recover my original signal exactly. This proves the sufficiency of the Nyquist criteria. If my original signal is band limited to between minus pi to pi, and if I sample it at a unit sampling rate, then I can reconstruct my original signal perfectly by first of all forming this reconstructed version as step 1, where I have just replaced my samples by Dirac impulses, and then low-pass filtering that signal, and that will give me my original signal back. First and foremost, this is a theoretical tool. It allows us to understand what's happening, but it also gives us ideas about how we might be able to do this in practice. In fact, if you have heard of upsampling before, you know that to upsample, the first thing you do is you introduce zeros between data points and then you low-pass filter. Well, that is very closely related to what we're doing here. Also, if we need to perform a digital to analog conversion, then this idea gives us a first idea of how to go about doing that. I can create a spiky output like this, approximately. I can't exactly have a Dirac delta function, but I can approximate that, and then I can low pass filter it, and maybe that would be a good digital to analog converter. It is also useful to note that if we sample in time and then set the gaps between our samples to 0 in this way, then we create a frequency spectrum which is periodic. For example, by time-frequency duality, this suggests that if my original signal is periodic in the time domain, then maybe in the frequency domain it consists of these discrete samples, like in this case here, and we will find that this is indeed true. And this leads to the idea of a Fourier series rather than a Fourier transform representation for periodic signals. To summarize, if we start with a continuous time signal x original of t, which is band limited, meaning its frequency content is limited to being strictly between -pi to pi, here I'm assuming unit sampling rate, then if we sample this signal, form the pulse train signal by replacing individual samples by Dirac impulses, low pass filter this with an ideal low pass filter, then we perfectly recover our original signal. In general, regardless of whether our original signal is band limited or not, the pulse train that we form at this step has got a Fourier transform given by this equation here. All we do is we take the spectrum of our original signal, shift it to the left and right in units of 2 pi, and add all these copies together. This is exact, irrespective of what our original signal is. From this, we deduce this sampling result for band-limited signals, because then, when we perform this summation, all the other copies are not going to pile on top of each other, and we can still recover our original signal by low-pass filtering the pulse train version here. Going one step further, we can ask if we can do this reconstruction purely in the time domain. So the frequency domain is what allowed us to work out what was happening and how to do it, but then we can always take the inverse Fourier transform and work out a direct expression from how to go from our sampled signal to our reconstructed version. In particular, all we need to do is realize that our reconstructed signal is given by the convolution. This is where we do our low-pass filtering. We convolve our pulse train here with the impulse response of our low-pass filter. Now, the impulse response is simply the inverse Fourier transform of the low-pass filter. If this is an ideal low-pass filter, then it's given by what we call the rect function for rectangular, and we know that its inverse Fourier transform is the sinc function. And so we're convolving a Dirac pulse train with a sinc function, and whenever we've got Dirac impulses, they're normally easy to work with because they just pull out particular terms. And so by literally doing this substitution here, it's not difficult, and we get a formula in the time domain to reconstruct our signal based on using the sinc function to interpolate between points. Intuitively, sinc interpolation works as follows. Assume that I just have 3 sample points to make my life easier. The first thing we do is we fit a sinc function through each of these points centered at the time that they arrive at, by which I mean the following. At time 0, I need a sinc function passing through the green point. Now, a sinc function is going to be 0 at all our other sample points. That's its key property in life. Well, one of its key properties. And so it's going to come down here and be 0 here, and it's going to oscillate and come back up here. Similarly, on this side here. Now I repeat for this sample point here, so I need to have a sinc function that goes through this point here, and a 0 at all the other sample points. Something like that might do the trick. And finally, for this point here, I need a sinc function that goes through this point and is 0 at all the other points. Something like that. And then the final answer I get by just adding up these 3 sinc functions. In general, we'll have more data points, and so we will have more sinc functions to add up. Remember that at integer times, we will exactly recover our sampled signal because we get one sinc function that passes directly through our sample and all the other sinc functions are at 0 there. And in between sampled points, we get a nice smooth reconstruction, smoothed out by these sinc functions. Again, this is primarily of theoretical interest. In practice, there are often better ways of doing it, but nevertheless, this theoretical way motivates the discovery of practical ways that somehow achieve a compromise between a perfect reconstruction, which would use sinc functions, and something that's actually doable in practice with finite computation. We come now to sampling in the frequency domain. We saw that when we sampled in the time domain, we ended up with a periodic structure in the frequency domain. By duality then, we therefore expect that when we sample in the frequency domain, we will get periodicity in the time domain. For those that are curious, the time-frequency duality can be understood in two ways. The simple way of understanding it is simply that the formulae for the Fourier transform and inverse Fourier transform are almost identical. Therefore, what's true in one domain you expect to be true in the other domain too. The more complicated way involves a beautiful area of mathematics known as harmonic analysis and group representation theory. That theory explains this duality, and it also allows a more general concept of duality between more general signals, precisely functions on various groups. But for now, we just appreciate that because the Fourier transform and inverse Fourier transform look so similar, whatever happens in one domain should transfer over to the other domain. Mathematically, sampling in the frequency domain simply means we take the spectrum of a signal and we sample it at uniformly spaced samples, and that's the only information we remember. The blue curve here is our original spectrum, x of omega, and the green points are our sample points, and this looks identical to when we sampled in the time domain. Intuitively though, what does this mean? What does it mean to sample in the frequency domain? Is it only a mathematical exercise, or can we actually do this in practice? Remember that our ears are actually doing a Fourier transform. We can take an audio signal and put it through a bunch of parallel bandpass filters, thereby extracting the different frequency components of our signal. For those that notice these things, when we do it mathematically, we are extracting a complex number at each frequency, and we distinguish between positive frequencies and negative frequencies. In this diagram here, I'm dealing with a purely real signal, and therefore I write it like this. Now technically, we can actually split up this bandpass filter here to work out what's happening at the positive frequency and what's happening at the negative frequency, because the difference between these two actually represents a phase shift. So if we were a little bit more careful, for each frequency I can extract the magnitude of the frequency content at that frequency and also the phase difference for real valued signals. So if we have a real valued signal, the Fourier transform has got a special structure. This means we don't actually have to extract the complex Fourier transform for both positive and negative frequency, those four numbers, so to speak, the real and the imaginary components for the positive frequency and the real and imaginary components for the corresponding negative frequency. They actually compress into just two coefficients, which we can interpret as magnitude and phase. As foreshadowed, what happens when we sample in the frequency domain is essentially the same as what happened when we sampled in the time domain. In this diagram, the sampled frequency spectrum is given by the coefficients C of n. The sampling process throws away information. All we are left with are these green sample points here in C of n. The simplest thing to do with the values we don't know is to set them to 0, and so therefore our reconstructed spectrum is just given by keeping the sample values and writing them as Dirac impulses. Remember, the reason for this is because if I were to take an inverse Fourier transform, and if these were just finite values, because they're isolated, the integral would be blind to them and I'd just get 0. So to make sure that the inverse Fourier transform sees these values, I need to promote their values to being infinitely large, which is why we've got our pulse train of Dirac delta functions here. The key question is, what does our reconstructed signal look like in the time domain? Here is the answer, and it is the analogue of what happened when we sampled in the time domain. All we get now is that our reconstructed signal in the time domain is given by time-shifted copies of the original signal here. The minor differences have to do with the various constants here, and that's just minor detail. Conceptually, if we sample in one domain, then we get periodic copies piled up on top of each other in the other domain. The same reasoning as before then tells us if our signal x of t, our original signal, is limited in time, meaning it is zero outside of an interval, then this method allows us to recover the signal perfectly. In fact, what we will recover is a periodically extended version of that signal. To see that we get a periodically extended version, all we need to do is graph this function here, and we will see what's happening. Because we did this when we looked at time domain sampling, I won't do it again here. Nevertheless, this idea that we can convert a time-limited signal into a periodic signal is very useful, especially when we're in the lab. We are not going to wait infinitely long to finish recording our signal before working on it. Therefore, by definition, we are always going to be working on finite-length signals. In the lab, we start recording a signal, and then after a certain period of time, we stop recording the signal. If we are lucky, for example, if we're recording an audio signal, we might start with silence and finish with silence, which is the nicest case. If we are recording an arbitrary signal, it might be that we start at some non-zero value and finish at some other non-zero value, and these two values might be different. And that actually causes some problems. And if you're interested in that, you can read up about windowing in signal processing. Anyway, there are two ways of handling this situation. Let's assume that the signal I recorded will be denoted by x of 0, t, and we've recorded it from t equals to 0 to t equals to t0. Now, of course, if we're doing this in the actual lab, we are probably going to have a digital sampling here. But for now, let's just assume we've sampled in continuous time somehow. All our signal processing tools, which right now is just the Fourier transform, they rely on a signal x of t that goes on forever. So we have at least two choices on how we can extend x0t into a function x of t that's defined for all time t. One choice, and perhaps the most obvious choice, is to say that x of t is equal to our recorded signal whenever t lies in the interval of the actual recording. Otherwise, we set our signal to be 0. Often a more convenient option, though, is to extend x0 of t periodically. So intuitively, we extend it forwards in time and backwards in time to maintain the periodicity. Mathematically, the way we write this is just like the infinite sum we had before. So if I add a 1 subscript here, then I can define x2 of t to be equal to the sum as n goes from minus infinity to infinity of x1 of t minus n times, and the period here is t0. Because x1 of t is 0 outside this interval, this infinite sum here will give me a periodic extension of x0 of t. Sometimes a periodic extension makes perfect intuitive sense. If we are recording the sound of a steam engine performing constant work, then we do expect that the sound will be the same over time. It really is periodic. At other times, the signal does continue on. We don't know whether or not it's periodic. In fact, we don't know what it does outside the recorded interval, and then assuming it's 0 outside the interval is just as arbitrary as assuming it is periodic. The third case is if it really is 0 outside the interval we recorded. In that case, we can ask what is the relationship between our periodic version of the signal and the original signal, which is 0 outside the interval. Well, we just learnt that if we sample in the frequency domain, we end up with a periodic signal in the time domain, so we should be able to reverse the steps we did before and get an answer to this new question. Here's the precise question. I have a signal x of t, and it's equal to 0 for time less than 0 and greater than 1. So x of t is time limited to this small region here. If I generate a periodic extension of x of t, what is the relationship between the Fourier transform of x of t and the Fourier transform of x tilde of t. We know from earlier that if we start off with x of t, take its Fourier transform, then if we sample its Fourier transform at uniformly spaced samples and endeavour to reconstruct our frequency domain spectrum by replacing each sample by a Dirac impulse function, then in the time domain we have that x tilde of t is equal to periodic copies of our original signal x of t. Where are we? Well, we started with this signal x of t, which is time limited, and we formed this periodic extension of it because we were interested in doing that. And we asked, what is the Fourier transform of x tilde of t relative to the Fourier transform of x of t? We know from before that we can get x tilde of t by this other approach. Notice how this equation is identical to this equation. So one way to get x tilde of t, let's form a periodic extension of it. The other way of getting x tilde of t is to take the Fourier transform of x of t, sample it, reconstruct the spectrum by using these Dirac delta functions, and then take the inverse Fourier transform. Now, because x tilde of t is exactly the same in both cases, and because we've got uniqueness of Fourier transforms, we know therefore that the Fourier transform of x tilde of t must be big X tilde of omega right here. So we've answered the question. The relationship between our original x of t and our periodic extension of it is that the Fourier transform of x tilde of t looks like this guy here, which is obtained by taking our original spectrum, sampling it at these uniform samples, and replacing them with Dirac impulses. Remember, the Dirac impulses are simply because we have to boost the amplitudes sufficiently high for the integral to recognize them. This result is important to keep in mind for when you come to use what's known as the discrete Fourier transform. Normally, you're working with a discrete time signal of a finite duration. When you take the discrete Fourier transform, you are in essence implicitly performing a periodic extension of this time domain signal, and the result we have shown here on this page provides a theoretical justification for what you're doing here. This will be explained in part 3 of this video series. To summarize, if we have a signal in one domain, either time or frequency, and we sample it, then we get a periodic structure in the other domain. In general, this periodic structure is not obtained by just looking at the signal in a certain region and replicating it to the sides. Instead, it is obtained by shifting and adding the original signal to itself an infinite number of times. If, however, we have the situation depicted here where the original signal is limited, then the periodic extension is the same thing as this infinite sum. And that's why if we sample in the time domain, but the signal is limited in the frequency domain, it's band limited, then by low-pass filtering the signal, we can actually recover the original signal from its sampled version. A similar result applies in the frequency domain. In the time domain, it is common to perform this two-step reconstruction. Given the samples, we first convert them back to a continuous time signal by making each sample into a Dirac delta function, and then we perform a low-pass filtering operation to remove this periodic structure. So step 1, create a pulse train. Step 2, low-pass filter. While we can certainly perform these same two steps in the frequency domain, in practice, often this is not what is of most interest. Instead, the practical application of this sampling result in the frequency domain is that we are given a time-limited signal and we extend it periodically intentionally. We now know that this periodic extension of a time-limited signal is equivalent to sampling in the frequency domain. This is step 1 of the two-step process we mentioned earlier and helps explain why we explained it as a two-step process, because step 1 in itself is of interest. How does this relate to our bigger question? Remember, in part 1 we motivated a system of this form. Normally there would be a DSP block in here, but we said if we can't even recover our original signal at the output here, we're going to have trouble doing anything interesting. It suffices to understand the A to D converter as performing sampling. Therefore, it is the job of the D to A converter to perform the reconstruction. What we have just learned is that reconstruction is possible under certain situations, at least theoretically. Precisely, if x of t is band limited in the frequency domain, then we can reconstruct it by taking our samples, converting them to a train of impulse functions, and then low-pass filtering. In practice, a D to A converter could attempt to approximate this procedure. It cannot create a true impulse, but it can create an approximate one, and then it can also low-pass filter it, not with an ideal low-pass filter, but with an approximate one. Going further into the theory would allow us to understand the errors caused by these approximations and then lead us perhaps to a better design of a D to A converter. In closing, we now know that if we have perfect A to D and D to A converters, then we can exactly reproduce our signal x of t at the other end, and that means that we can also introduce digital signal processing algorithms in the middle here, and they get the full information there is available about x of t to work with. So anything we can do in the time domain, any processing of x of t we can do in the time domain, we can now also do in the digital domain due to this sampling result. So the sampling result is fundamental for the theory for this to even exist, but it's also very important when you go further and try to understand the effects of the A to D and D to A converter not being ideal.